Hello, and welcome to Lesson 8 of this Introduction to Linear Algebra with Wolfram U. The topic for the lesson is the matrix of a linear transformation. So let's begin with a brief overview of the lesson. So in the previous lesson, you learned that every matrix defines a linear transformation. So for example, here is a matrix. It's a 2 by 2 matrix. The first row is 2 and 3, and second row is -1 and 5. Now this matrix defines a linear transformation T, which is given by x goes to A dot x. So here's the linear transformation T. And the goal of this lesson is to show that in fact the converse is true. Namely, if you start with any linear transformation, then you can find a matrix that is associated with it. And once you've done that, then we'll use this idea to associate matrices with reflections and other geometrical transformations. So let's begin with the motivating example. So here is a transformation T, which is given by T of x1, x2 is 4x1 minus 3x2, negative 11x1 plus 9x2, and 2x1 plus 13x2. Now, if you look over here, we have these two unit vectors 1, 0, and 0, 1. So what we do is we try and find the images of these vectors under the transformation T. And when you do that, you get back the results, each of which is a 3 vector. And then what you do is you form a matrix A whose columns are given by these images. So here's the matrix A, and you can see quite clearly that the first column is the image of 1, 0, and the second column is the image of 0, 1. And this matrix is the matrix associated with the linear transformation T. So if you check the result with T itself, you see you get back just the same result. So that's the idea behind forming the matrix corresponding to a linear transformation. So here is a more formal approach. So let's start with the linear transformation from Rn to Rm, where n and m are integers. So that's a linear transformation. Then there exists a matrix A such that T of x is A dot x for all x in Rn. Now, how do you form the matrix A? Well, what you do is the columns of A are given by the images of the unit vectors. So that's the matrix. Its columns are the images of the unit vectors. So A is T of E1, T of E2, etc. up to T of En. And this matrix is called the standard matrix for the linear transformation. Now, what we want to do is to use this idea to study geometric transformations. And in fact, we consider some common geometric linear transformations of the plane. And the fact is that these transformations can be determined completely by what they do to the unit vectors 1, 0, and 0, 1. Now, there are 4 of them for this class. The first one is reflections. You reflect, let's say, in the x-axis. You take a triangle, reflect it. You can dilate a triangle. You can shear it, or you can project points. So those are the kind of transformations we'll study in this lesson. So let's begin with reflections. So here is an example for a reflection in the x-axis. Now, if you look at the picture over here, you see that when you reflect in the x-axis, the unit vector 1, 0 remains where it is. On the other hand, the vector 0, 1 gets reflected in the vector 0, -1. So the matrix for this transformation is quite simple. It has its first column as 1, 0 because that's the image of 1, 0, and second column 0, -1 because that's the image of 0, 1. And now once you have the matrix, you can define the transformation itself by doing A dot xy, and you get back x, -y, which of course is correct because the sign of y changes under the reflection. And a second example for today, we talk about dilation by a factor of 3. So you have this transformation, which is dilation, and here's a picture showing what's happening. So if you look at the vector 1, 0, it gets dilated to the vector 3, 0, and 0, 1 goes to 0, 3. So here's the matrix. The first column is 3, 0, the next one is 0, 3. And then if you do a dot product, you get back the actual transformation 3x, 3y, which looks right. The third example for the lesson is horizontal shearing. So you have a shear in the horizontal direction by, let's say, a factor of 5. So this is a linear transformation. And to see what happens over here, we again have a picture. So look at 1, 0, nothing happens to it. But if you look at 0, 1, it gets sheared, shifted to the right by 5. So the matrix over here is going to be 1, 0 in the first column and 5, 1 in the second column. And if you do a dot product, that is the expression for the transformation itself. And finally, let's talk about projections. So you want to project onto the x-axis. Now, here's the picture. If you project 1, 0, you get back just the same result. But if you project 0, 1, it gets projected to 0, 0. So the matrix is rather simple. You have 1, 0 in the first column and 0, 0 in the second column. And if you do an algebraic expression for this, then you get back x, 0, which is of course correct because every point kind of loses its y coordinate and remembers x coordinate when you project. So when you project down over here, you get back just the x coordinate. Okay, so with that introduction to transformations, let's go a little deeper into transformations and talk about one-to-one linear transformations. So here is a transformation T with a standard matrix A. And the question is, when is this transformation one-to-one? Well, T is one-to-one if and only if this equation Ax equals 0 has only the trivial solution. Now that's a bit easier than the general case of one-to-one functions because A is kind of a linear operator. So let's say you have a transformation given by this matrix over here. You want to check if it's one-to-one. So what you do is you look at the homogeneous equation Ax equals 0 and form the augmented matrix, row reduce it, and you see over here that actually have no free variables. The first 3 columns are just what they should be, and so you only have the trivial solution 0, 0 for this homogeneous system, and hence the transformation is one-to-one. So checking if a linear transformation is one-to-one is much simpler than for a general function because you actually only have to solve a matrix equation, namely the equation Ax equal to 0. Okay, on to another kind of transformation, which is onto transformations. So here is a transformation T with standard matrix A. The question is, when is it onto? Well, if it's onto if the columns of A span the image. So here is your matrix A, let's say. And what you want to do is to check if the transformation T, for which A is a matrix, is onto or not. In other words, if you're given any vector in the image, Rm, over here, in the codomain, then can you find a pre-image for it or not? Okay, so let's do a row reduce. That's the matrix form. And you see over here you have 2 independent columns. So the columns of A span the plane, and hence the transformation is onto. Okay, so let's check that with linear solve. And you see that for any vector b1, b2, you actually do have some vector which gets imaged onto it, transformed onto it. And you can check the answer, and you see you get back b1, b2. So checking that something is onto is quite simple if the transformation happens to be a linear transformation. So 1, 1 and onto linear transformations are much simpler than arbitrary transformations of the plane or other RMs. Okay, so to summarize, there is a standard matrix A for any linear transformation T. And how do you find A? Well, the columns of A are the images of the unit vectors of the domain under T. So you form the matrix A by forming the columns. Now, given a common geometric transformation, such as a reflection or a dilation or a projection, you can find its matrix quite easily. A linear transformation is one-to-one if and only if the homogeneous equation over here has only the trivial solution. So that's a very easy way to check that a linear transformation is one-to-one. Also, it is onto if the columns of A span Rm. Okay, so that's a summary of this lesson, and in the next lesson we talk about matrix operations such as addition and multiplication. But the main point over here is that given any linear transformation, you actually have a matrix associated with it, and that's quite a big advance in linear algebra for us. So I'll stop over here. Thank you very much.